Greetings, everyone. Rick Cole here from RDSEA International in Florida, along with my colleagues Jeff Donovan and Dennis Mayer at the University of South Florida's Ocean Circulation Group. We are here to talk a little bit about ADCPs on buoys. We thank Teledyne RD Instruments for inviting us to give you a brief overview, very brief, of some of our experiences of collecting data from surface buoys with downward-looking ADCPs. There's something that's it's very, very challenging, not to say the least. We understand that we're putting an ADCP on a moving platform, but you really have to start to understand what's going on in the arrangement with depth versus frequency. But at the end of the day, what's really important is understanding what to do with the data once you recover. There's a lot going on there in post-processing. This was our very first attempt back in the early 90s out on the West Florida shelf of Eastern Gulf of Mexico. We took one of our Pacific narrowband 150 ADCPs and we inverted it and installed it in the buoy bridle downward looking. This was a 50-meter location just north of Tampa Bay. This was the first attempt at doing this. And the thing about the narrowband ADCP is it has a 30-degree spread on the beam pattern, and that gets the energy away from the mooring line in a nice clear manner. And what you can see here on the left, these are contour plots of U and V, and they came out very nice and clean. There was very little massaging that had to be done to this data set. And over here on the right, we have our vector plots. This is a nice, clean, near full water column set of bins. Again, it was a 50-meter site, and we have just about 40 meters of data. In the early to mid-90s, RD Instruments introduced the workhorse ADCP, a variety of frequencies. So this changed the way we process data immediately due to the fact that the beam pattern is now 10 degrees less. And we also started mounting instrumentation on the mooring line, which ultimately would cause problems when we're looking at that post-processing of the bin data. This is a schematic pulled from the workhorse manual, which clearly shows the cone and the cone of side lobe reflection and that beam pattern. And you can see right here, this text down here actually says, please do not put obstructions in this region. Well, again, that the energy from each beam is going directly down the mooring line. So here we had to definitely do some very serious thinking on redesigning our buoy bridle to not obstruct any of the four beams. This was a design that a group had wanted to do using an older style of buoy bridle, and you can see that clearly that's going to affect beam 1 of the data. Here we break out each beam, 1, 2, 3, and 4. Again, this was for a 25-meter mooring location, and here we see the surface in the beginning of the data set, and then down here is we're hitting the bottom, and this is our side lobe reflection. You can clearly see we are picking up the mooring from each beam, and these little nodes here are CTDs along the mooring line. This is the raw data set without any additional processing of U and V, and you can clearly see the bottom. That's these white bubbles, and then these horizontal green marks are the CTDs on line. Now, once that data is cleaned up in post-processing, we actually are extracting out those biased bins that we're picking up from the CTDs, and you can see here we have a nice clear contour of about 20 meters of that 25-meter location. In the latter part of the last decade, 2009, RDI introduced the Doppler volume sampler. This is actually a single-point current meter that actually profiles out to 5 bins. So you can see that we're now adding continued interference within our data set. Well, we first tried to install these on the mooring line side by side, but hardware was not allowing us to do that, so we had to go top and bottom of the CTDs, which was going to add continued interference on that data set. And here it is, again, beam 1, 2, 3, and 4 pulled out from the data set, and you can clearly see the CTDs and the DVSs are picked up in beams 1 and beam 3, and along with the mooring throughout the data set. This is the cleaned up version of the comparison data set. The top panel, this is the V component, top panel, north and south direction. This is the DVS, and then this is the downward-looking workhorse that's in the center of the bridle. And you can see there's excellent correlation between both instruments. At the end of the day, what we decided that bottom mounting the ADCPs is clearly the better way to go. So in a perfect world, we would decouple the ADCPs from the buoy and bottom mount them aside from a surface buoy in this fashion here. Back when Neil Treneman was still working with RDI, we had a dream at USF of testing horizontal ADCPs on the buoys and then also down at the bottom mount, the bottom boundary layer, removing the ADCP from the buoy, bottom mounting it again, and then replacing that with acoustic modems to get the full coverage without any biased ADCP data, and that also allowed us to mount as many CTDs in the water column as we possibly could. If you go to the Ocean Circulation Group's webpage, here's the link right here. You can pull up a very, very nice data comparison between downward-looking ADCPs and upward-looking ADCPs. Weisberg et al. That is there to pull out for review. It's a very, very excellent data set. And again, as we said, at the end of the day, if you are planning on mounting ADCPs on buoys, it's best to contact those that have already done it so you don't have to reinvent the wheel and really question what all has to be done in that post-processing. There's definitely a lot to it. We thank you very much for listening, and good luck.